Mic check.
Seems good.
Yes. Just something about the story from the 1980s when Ronald Reagan was president of the US, and they got him to do a sound check. He told him just say something just to make sure the sound systems work. And what he chose to say was, "Let's bomb Russia."
That's not right. Definitely.
I mean, somehow they find a way to land it off, but it was, it caused diplomatic flutter.
Say something not that.
One, two, three, or Mary had a little lamb, or one of the usual ones, right? Right.
Okay,
So the categories where the objects were categories and the morphisms were functors. And now we're going to build another category and establish, which is going to have less structure. So let's see if we can figure out what it's going to be. It's going to be the category of relations. So thank goodness we have type and type, because the objects, I think, aren't the objects here going to be sets?
no, I think we're doing raw burster style with relations as objects.
As the objects. Okay.
Yeah, so we have a double of a set and a binary relation on that side.
Binary relation.
Yeah.
Okay, sure.
And then we are going to get our three categories as
Okay.
the functor from that. Okay, so we will have as objects arbitrary sets with a relation on them.
Right. And
then given to such objects, so again, that is just a set of relation.
yeah,
Better rename that.
yeah. What's the only? There aren't very many things that make sense. I'm supposing it's a function from one set to the other that preserves the relation.
Yes. And
So map from the set before to the set after, and if the relation, if we've got two elements which are related before, they should be related. Well, we haven't said anything about what has to hold about the relations, and we're not going to.
You showed the holes have to be monotone.
Well,
Relations are.
they have to preserve the relation, but it's not necessarily important to think of the relations in some sense
Related.
as having any structure to them, like they're not. there's no particular reason. We don't have in mind any particular flavor of relation or any properties of relation. Okay. So we want to figure out how to build the identity
So,
on a given A and R. So expose. But we got the identity function, and we should hope that if the relation holds and we of an A and a B, and we do exactly nothing to the A and the B, then the same relation still hold. So, not a shock. And we should also not be particularly surprised to find that if we've got three sets with relations on them, and we got functions which separately preserve the relation, and composition is going to behave sensibly. So here
we can also call comps
set G, and then this is going to be.
So we have X, and we see
That's the
B.
It says that A is related to B. P will get us that F of A is related to F of B, and then we can plug those things into Q. Get that. But you can see what we're asked for is that G of F of A is related to G of F of B in the relation that corresponds to our third thing. And we can, so Q is going to get us to G of something, and then we're going to plug in what comes out of the P. So, funnily enough, it's composition of functions and composition of preservation proofs. I mean, this is just the appropriate notion of composition for that stuff.
And the comp set FG is a G circ F, right?
Yes.
The other way around.
It's it's a habit to keep things diagrammatic.
Yeah, I double checked this myself.
Yes. Okay. And then what's more, what we got here is essentially that we're working with pairs of functions and ordinary function composition, which is orthogonal entities and is associative on the nodes. So these should all be relevant.
Indeed, and you might be wondering why we were writing ID set and then giving the explicit identity function, but I think this is purely for semantic reasons. Our first component is actually something living in set, and the second, as Connor said, is talking about preservation of proofs and preservation of properties. So yeah, it is essentially the same as identity, but it has a bit other meaning in our domain rather than, okay, this is identity of the set.
And it's got a couple of implicit quantifiers knocking around that we are purposefully ignoring.
Maybe that will bite us later on, but let's see.
Extra line there. Okay. So let's so we know that categories have objects and morphisms, which could be, I mean, it's the right the right data for one of these things. So we should be able to take a category here, say that the objects and morphisms are a set and a relation in that set, effectively. So what we're getting is that the morphisms obey the laws of category. Some family of sets next to a pair of objects.
I'm confident it's three categories. Upstairs.
Right. So then,
What would be our action on functions? Well, we don't have that much choice now.
yeah, we have to first sort of think about what happened in categories. The map operation says if you've got more of a source category, then you have to take it to
This is back there, so that's not that, right?
yeah. So exactly plugging in the machinery, but just as we've forgotten that we need to have special structure in the density composition, we are forgetting that we are obliged to preserve that extra structure. So all we're doing is chucking morphisms around. Okay.
Maybe that would be better.
So yeah, so here we do have a bit of work to do, but not much.
So that should have been put in as you refresh. And it should be converted.
Yeah. So here we're basically, so if you think about what was going on with our with the machinery and the function category, you know, the density and composition is always the identity action and composition of the actions presenting map composition maps. So so it's the same. We're doing the same thing with the underlying machinery. The only thing that's going missing is the structure of the proof that it's respected. So yeah. So here. You know, those things are the identity function, and we just made where we're going to. We chose the identity operation for the identity, and likewise, what's going on here is, you know, this is composition of functors, which is composition of the actions, composition of the maps. And we're targeting something which again is still plain composition of stuff. So we should not be surprised that this turns out to be right. Because we have kept the operational machinery but forgotten the lawfulness. So this forgetful functor operationally does exactly, well, what it preserved, what it retains, it does nothing to, just discards other stuff. Okay, so there we are.
And maybe we need to take a step back and realize why do we need that category. So we got our forgetful functor and we're on the verge of defining our free functor from rel to cat. But why taking this most strange category of relations? Why didn't we take sets and relations? And if we had done that, think about what kind of category we end up with, right? So we are given object in set, and we need to turn that object in category, but it's going to be a bit too boring, right? Because what can we do? Essentially, we can add the identities, and that's pretty much it. So from a set, we can get a discrete category that has all identities and no other morphisms. But now we have already anticipated that, so we did something a bit more useful and a bit more interesting. Now our objects are actually relations, and we can enhance these relations to be categories. And by enhance, what do I mean? So we have to make sure that categorical worlds are preserved. That is, there's identities, so the relation is reflectives, and for any two morphisms with matching domains and codomains, so for any two morphism from A to B and B to C, we need to add the composite. So this is making sure that the relation is transitive. And in order to do so, we can have a data type that models the reflexive transitive closure of a relation.
Yeah, so this basically says, you give us a relation, we're going to kick it into this category.
What is it star?
It's called star by analogy with the clean star in regular expressions. So that's to say, just like, so it means zero or more of this thing. And what we're getting zero or more of is steps related on R. So you can think of this, what a good way to think of it is that R tells you, okay, yes. That, you know, R might be, you might actually think of R as being, you know, an actual collection of, oh well, I might draw another one like that. That's always the danger. Yeah, so this, you know, our set might be the set of these three points. And, you know, it might be the case that between this point and this point, there are two elements in R. Between this point and that point, there's one, and between here and there, there's none. What we are then doing is completing this picture to make a category. So so you have to add this one, that one, and all the densities.
So what is the relation to that? That's about it. So we basically said we're throwing in the identity. Yeah.
So there's always a path from any object to itself.
If we have one to start with, construction one, construction other.
Yeah, and if we take one step from A to B, and we can carry on with 0 or more steps to get from B to C, then we can get from A to C. These are paths. You can just see them literally as paths along the black edges.
This are exactly the frame category.
Yeah. So, so what we're going to do is, someone gives us a relation, and we are going to star it.
Okay, so for the objects, okay,
Yes. Yeah.
so here we actually have to define a category, and let's use copatterns again.
So the objects are going to be A, and what business are going to be?
Let's make them R and see why we need the star.
Okay. Let's see what goes wrong. Right. So here,
These are your current identity.
yeah, we don't know anything about it. And we need to get identities somewhere. So,
So we're stuck now
yeah,
pretty fast, which is good.
if we artificially throw in the identities, then we're good.
And then if A&R would work, would we say a relation of categories?
We will do this, but not so.
Not so.
Are we really going to do this? Or pull it up.
Well, pretty bad here.
So you should expect, even if the type looks kind of extremely familiar, extraordinary sense of deja vu. One of the things that's really noticeable about the library of any dependently type programming language is that it tends to require a myriad of data structures which are fancy varieties of lists, whether they are lists with a statically length, or whether they are lists are ordered, or whatever it happens to be. There's just a gazillion list-like structures, and there's exercise, at the very least, show them up as
Could they all be done that way?
they do all collapse. Yeah, simply because this the free category is abstracting over disciplines for which edges are allowed. I gave a talk about this at a meeting in York in 2005. And I was extremely careful to talk about it in the language of good old-fashioned functional programming. I was talking generalizing lists. I was very, and so looking at what math was like, I was very careful not using any categorical terminology whatsoever. And I could see the category theorists in the audience getting very itchy indeed until one of them couldn't hold it in any longer.
So that's 3 seconds in.
Yes. Yeah. Isn't that just the at which point I slapped on a slide which said, "Don't let the cat out of the bag." But guess what?
So
It is just
Yes. But even so, you went on.
just to make sure that this goes through.
Battery power. It's score extreme jeopardy.
So what's star called in general? Is it not called star? The standard edition?
It's sort of zero or but yeah, people would call this the thing. Yeah, locally, I think we.
Well, if I was to look into a category theory, that would look more difficult. And not the computer science category.
Probably it would be called the free category.
Oh, well, relatively like,
Yeah, but
we're sort of using it to avoid.
but it's quite normal to consider. I mean, people often write star, a postfix star is a list. Right, X star is the words on the alphabet X, otherwise known as lists with X's as elements.
The three word.
Yes. So, yes, the free monoid, this is the free monoid.
Every category is a word.
Right, so here we are doing what? We are
Defining a function.
what is to be
Free category over the relation X.
so the free category over the relation Y. So we better be able to give a function element to element, explain what sort of coherence we're expecting. And then here we're saying we've got a path whose edges are given by our first relation, X relation, and we need to turn it into a path in the Y relation, but we know how to transport individual edges in a way that fits with what little f does. So we should be good for that.
We don't know that yet.
So here's Right, we've got we're about to farm it out as a so this really says that we start from one we start with preserving the individual edges, and then we have to look at that to preserve the parts. So you can see here, F says what happens to the points, P says what happens to the edges that connect the points. If A and A prime are connected in R, then their images are connected in Q. Correspondingly, we should be able to write an extremely familiar looking operation. If we start with the identity path, then we should be able to construct a corresponding identity path. And if we take a step in the R relation, we should be able to take the corresponding step in the Q relation. Yes. So P of X will get us from F of A to F of something. And we need to get the rest of the way, but we can process recursively. So, shock horror, append turns out to be fancy append, map turns out to be fancy map.
And indeed here. We can use that, and here it is where our choice of implicit arguments doesn't let us immediately put P, but
Yeah.
it let us do that.
Okay. And since what's happening is that we are just applying the same function everywhere, we should not be astonished. Here, we exactly need to show. So the first one, the identity property, was mapping across the empty path. And here we have to show that map commutes with concatenation.
Generally, you can just copy the definition from the list and it works all the same.
Yeah. I think that is. Okay. All that's happened is that everything we learned with lists, like using Jude-Low Lego when you're 2 years old, still works with proper Lego when you're 6. Many years before Agda even existed, there was implementation of dependent type theory at the University of Edinburgh, which used food decided to call Lego. They threatened to sue us over existence.
How long did it take them to do that?
About 10 years, they were only just beginning to get into computer software and set up a website and that sort of stuff. And they did a quick search, and they found that we could temerity to have a website and to be calling ourselves Lego or something still at the time.
And so it was also like the concept Lego.
Exactly, I mean, it was a whole
It
man.
makes it even worse.
But yeah, and I told that story in a talk that I gave at a meeting about 10 years ago, and women in the audience started to laugh, and she explained after I told the story that she'd been a student in Denmark at the time, and her then boyfriend had been the lawyer of the ledger, and that they were deadly serious about newness and orbit. So it's a very small world. Yeah, so this is going to take.
Yeah, I was hoping that we wouldn't need.
To, it's
Yeah.
one of these things where implicit, explicit plumbing rules are puzzle. Right. So I'm gonna be,
We have to prove equality of functors here. So
time. Sort of okay. But that's gonna be, once we get done saying, look, they're equal at the same machinery, we know they have the same machinery.
Common-sized Jesus.
Is that one going to involve? That involves some work, that one, I think.
does it? Yes.
Yes, it does. That's going to involve. Deal with it. Extensionality. Because we actually have to do induction for our math, saying like, if we do nothing to each individual edge in it, that's the same as doing nothing to the whole thing. And then the next one is going to be another induction, because it's going to be like, okay, we've got a path, and then we walk through the path, doing F through all of the edges, and then we walk through that path, do G to all of the F edges, then that's the same as doing F and G to all the edges. Another chunk of induction. Is that one you prepared earlier? Yes.
Yes.
It's a bit of a mouthful because there's just so much stuff, but it's not a surprise. It goes the way you think it's going to go. With a suitable calm.
That makes life easier.
Yes, well, you're
not
lucky
the
because,
best.
because this is a constructor.
Yeah.
It's going to be able to solve the equations with magic.
Let's actually ask the solver.
Yes. Right.
Okay. We're not that lucky.
Yeah, the type of this thing leaves a hell of a lot of implicit. You're going to need to extract all sorts of things.
Yeah.
Maybe part two. Which you figure out how to wind up.
Well, by fixing the implicit sounds like a good. You could just briefly sketch what's going to happen on Thursday then, with getting the free injunction.
Yes, so we're going to show that this construction, so our forgetful function was for getting the structure of the category to give us back a relation we know nothing about, and what's happening here is that this construction, which chucks in exactly the right stuff to an existing relation to give you back a category, is going to be the left adjoint to the forgetful thing. And is going to give us some even more interesting as well. You know that the lists form a monad, where the return singleton lists, and the join takes a list of lists and flattens it. There's one layer of this. We are going to be able to play exactly the same game here, where if you single edge, you can make a path of length 1. And if you've got a path whose edges are themselves paths, you can combine those two layers into one. And I mean, it's exactly the same machinery. It's just,
Take policies, examples out of
yeah, so if you've got star and star R, so and indeed, at some point, I don't know, did I miss? I did miss it. So there's going to be, what is all of this? What does all of this adjunction business have to do with IELTS? It's, I think, where Fred's heading for.
We believe you that it was.
Yeah, yeah, yeah.
Yeah, we should, because the next class for this room already on our heels. Just handed out on the table.
Okay.